So this is a re-recording of the Laplace transform in circuits. That's my first video for the class of 422. And the reason to use Laplace instead of phasors or differential equations is that they are, of course, much easier than differential equations. They are just algebra. And for phasors, we can only use sinusoidal input. Well, I guess we could scramble a DC source there, but in principle, we can't assume different initial conditions. They're always zero. So Laplace is a much more general method of solving it than phasors. It's as general as differential equations, but much simpler. So a lot of things happen in electrical engineering that are not phasors, and they make differential equations super complicated. So Laplace is definitely the solution of choice, including signal processing and control. So you're going to use this in other fields of electrical engineering. It's not only circuits. So here I'm going to show you how to use components in circuits that include initial conditions. So this is the main thing in this video. From now until the end of the class, we're going to only talk about Laplace. And if there were circuits 3, you'd be seeing Laplace all semester long. If you go to a job interview and they ask you just say what the most important thing in circuits is, there is a chance you'd say Laplace right after Ohm's law, V equals IR. So that's what I wrote on the top right side. Kirchhoff's law, nodal, mesh, these are all less important, I think, than Laplace. Laplace is only second to Ohm's law, maybe. V equals IR or V equals ZI. Now that we're using impedance, which is any of the resistor capacitance or inductances. So now we're going to go back to what we learned in 285, which is V equals L di dt, and it's the voltage across the inductor, and it's the derivative of the current through the inductor. Here I made a typo, I wrote L. And now we're going to do the Laplace transform. And as Albin wrote in the previous video, or the video last week, we can do the Laplace transform on both, and it's the integral from 0 to t of that function times dt, of course. And to do the derivative, then to comply with all the math that you guys learned, we're going to say the V of S is the inductor times S times I of S, which is the Laplace transform for the derivative of I of t, minus I of 0. That's the initial condition on the inductor. So now I'm just going to write the inductance times those two factors. And the first one is what we had for phasors, right? So the voltage across the inductor is the sum of the Ls times I of S minus a voltage that we're going to now draw as a voltage supply, L I of 0. So the first part is what we knew anyway. I'm going to draw that first. That's the inductor. And in the S domain, the inductor is going to be Ls. And now the voltage across the inductor is all this. It's the initial condition, which is a voltage supply, in opposite direction to the voltage across the inductor. Plus the voltage that's SL times I of S. So this voltage supply here is L times I0. We can now do, for example, the source transformation of this circuit into an inductor in series with a current supply. When we do the source transformation, we're going to use the same method as we did in 285 and as in the phasors in 286. We're going to assume there is a current through that circuit. And I'm going to draw a current supply. And now the direction of that current supply is going to go down. The arrow is in line with the plus on the voltage supply, and the current will be the voltage L I of 0 divided by SL. So it's going to be I of 0 divided by S. These two circuits are equivalent. Alternatively, I can also do this by manipulating this equation here. And instead of writing VL of S, I'm going to put out the I of S. So I want to write I of S, yes, it's the current. And I'm going to put VL on the other side and LS as a denominator. VL plus L of I of 0. And then the denominator is going to be LS. And then I'm going to simplify this. And you're going to see that this is exactly what the drawing of the source transform is. So IL of S is that V L of S divided by LS, which is the impedance of the inductor, plus I plus I of 0 divided by S, because the L's cut. So these two are these two circuits are going to be used when we draw Laplace circuits with initial conditions. So if the initial condition had been 0, those two power supplies would be gone, either open or shorted, depending on if they were parallel or series. But here you see for the first time how we can use these. The Laplace transform is the only new concept in this class. Is this use of initial conditions in both inductors and capacitors. So in the next video, I'm going to show you how to do that same thing with a capacitor.